of our understanding to the next level, right? You will talk about the proof of Kahn-Kalai conjecture. Please.
Yeah, thank you very much. So this is a continuation of the last lecture, and so today we're going to talk about the real math, not the fake math. And yeah, because this is already yesterday, so let me remind you our definitions from the last lecture. So this is called. Can you see here? Okay. So we used X for a finite set, and we used mu p. This is the p-biased measure, and the definition is p to the size of a times 1 minus p to the size of the complement of a for any a subset of x. And we used xp for the random variable whose distribution is mu p. So xp is basically the p random subset of x, where p random means by a biased coin flip. So for each element, we toss a biased coin and independently. And I introduced another notation. So this is not xp, and we use xm, where m is a natural number or an integer. So xm is a random variable, but this is chosen uniformly from the collection of all of the subsets of x of size m. So we just choose any m. We choose an m subset of x uniformly at random. That's the definition of xm. Okay. So if you have any questions, then please stop me anytime. So I planned this lecture. My lecture notes is for 1 hour, but I need 2 hours, just to allow, not to torture you, but just to allow many questions and discussions. So please stop me anytime.
So xm is the same as x half, or no, of course not. Sorry.
Thank you for your confusion. It helps people to relax.
Probably xp and xpn within the size of x also behave roughly the same.
Oh yeah,
Yeah,
roughly,
like
yeah. So that's yeah. So we are
okay.
gonna use that to reformulate our main theorem. Yes, that's right. Okay, and then we use this calligraphic f, this in 2 to the x, and we used this for an increasing property. And roughly speaking, on increasing property means we cannot destroy this property by adding an element. So the formal definition was whenever B contains an element in F, this implies B is also a member of F. This is formal definition, and so I drew this picture yesterday. So F looks like this, which means whenever we have an element inside F, then everything that contains this element is also in F. That's the definition of an increasing property. And we saw this graph. So F is always an increasing property, and as P increases from 0 to 1, mu P of F, this also increases from 0 to 1. And then we defined, so because our random object xp satisfies the given increasing property F. And if we are above the threshold, then it's much more likely that xp satisfies the given increasing property. That's the definition of the threshold. That's a rough meaning of the threshold. And then we define the expectation threshold. And for this, okay, let me introduce another notation. We're going to use this bracket A, where A is a subset of X. This means simply everything that contains A. So this is the collection of B, where B contains A. So in our 2 to the X picture, in this picture, is where when A is here, the bracket A is this. This is a picture of bracket A. Okay, so simply this is just the offset generated by A. Okay? And we had this observation last time. So this observation was about a lower bound on the threshold. We said P PC of f, the threshold is always bounded below by p if there exists a hypergraph u. I changed the character. I changed the letter. If there exists something called u into x that satisfies two properties. And yeah, I don't know if you still remember that, but let me assume for our safeness, let me assume you don't remember that. So the first property was so-called u covers f, and this means in pictorially this means if f is here, then u looks like this. So if we consider the offset generated by u, then this contains the increasing property f. This is the meaning of u covers f. So f is contained in the offset generated by u, which means, so this is defined by the union of u in u and the offset generated by u. Okay, and the second property was, let me call this u is p chip. This is a new notation, so when I say p chip, this means if we add up p to the size of u for every u inside u, this is at most 1. So if p admits such a hypergraph u, then this p always gives a lower bound on the threshold. Okay. And here I used this p chip because this expression depends on the value of p. So, and then our definition for the expectation threshold. Oh, yesterday I wrote the expectation threshold PE, but today I changed the notation just for my convenience because it's annoying to write down PE every time. So let me just write QF for the expectation threshold. Okay, so this is defined to be the maximum of P that admits U that satisfies the two properties. The first one is U covers F, and the second one is U is P chip. Okay?
U, that is P chip, right?
Yeah, U, yeah, so U, yeah, the U is P chip. So this cover, so again, this is the meaning of U is P chip. So that means if we add up P to the U for every member in U, it is at most 1.
So what does it mean?
Oh, it's just notation.
But,
So this means if we add up P to the U for every member in U, then this quantity is at most 1/2. That's the meaning of U is P chip. It's the definition.
But is it possible to say some
So-
translate it combinatorially somehow?
Combinatorially,
Like when it's cheap for smaller p or for larger p, what does it mean?
so for example, if P is very large, then this cannot be satisfied. So this is more preferable if P is smaller. So that means if as we increase P, so U is given, for given U, when we increase P, then this gets larger and larger. So at some point, this cannot be satisfied. So basically, this P is the maximum that satisfies this property. And so that maximum P gives us a lower bound for the threshold. And so our definition of the expectation threshold was so for each cover, we can find a good lower bound. And that lower, so because we want to find a good lower bound, so we will increase P.
So you actually want to find a cover that's not so cheap in some sense, right?
That's not, yeah, it depends on P. So we want to increase P. So we want to find, okay, so we want to find the maximum P because we want to find a good lower bound. So we want to find U that achieves large P in this, as long as it satisfies this P chipness. Okay. Okay, are we happy? Okay, and then let me give the statement. The theorem, so this is the Kahn-Kalai Conjecture. It says there exists a universal constant K such that for every finite set X and increasing property F, the threshold PC of F, this is at most K times the expectation threshold times log of L of F, where L of F is defined yesterday, but let me write it down again. This is the size of a largest minimal element of F. So pictorially, if F looks like this, then we consider all of the minimal elements, and then we choose the maximum size of among all of the minimal elements. So the size of this element is L of F this time. Okay, so this is the statement of the Kahn-Kalai conjecture of what we are gonna prove. What we are gonna actually prove today is a reformulation of this theorem. So let me give you another statement. So this is a reformulation. And in this reformulation, we can think of this as, so we are going to introduce another hypergraph H, and basically this is just the collection of all of the minimal elements of a given increasing property F. So basically we change our viewpoint. Instead of looking at the entire increasing property F, we just focus on its minimal elements. Okay? And then we can say two things about this hypergraph H. The first one is, this one is L bounded. This means every element in H has size at most L. So that corresponds to our definition of L of F. So this is the first property, and the second property is, of course, what happens if we consider the offset generated by H. This is exactly it starts with F, yeah. This is exactly F. Okay?
Can I ask you something? To understand this expectation threshold, can you give some example? So I remember that last lecture you gave an example of a diamond-shaped graph H.
With a tail.
And its expectation threshold is n to the minus 4 or 5. Then how can you obtain this bound with this notation?
Oh yeah, so this one, you mean this definition?
Yeah, in this definition, how can we get the expectation threshold?
I showed that last time, but it's okay because we have 2 hours, so I can.
But with this definition.
Yeah, so this is the definition that we used last time. So for example, if our, do I have a space? So let me make a space. See, 2 hours is useful. Okay, so so last time in our example 2, F is to contain this graph. Okay, so this means in this 2 to the x picture, F is supported by all of the minimal elements are the labeled copies of K's. And then F looks like this. This is F. And so there can be many different covers, right? Whenever we choose something below these minimal elements, and then it can be a cover. So the first candidate for first cover that we chose last time, I called that G1. Well, let me use U1 this time because we switched our letter. U1 was the collection of all of this thing, right? And in this case, of course, this satisfies the first property. And in the second property, we want to say U is P chip, and this computation is basically P to the size of U, but here size of U means the number of edges inside this copy, because our ground state is n choose 2, not the set of vertices. So in this case, the size of U is 1, 2, 3, 4, 5, 6, so we have P to the 6. And then this sum corresponds to the number of potential copies of K's in the complete graph. And because we ignore constants, so this is more or less n to the 1, 2, 3, 4, 5. And we want to say this is at most 1/2. Okay, so and because as I said at the beginning, so we want to find the best lower bound. That means we want to find the maximum P that satisfies this inequality. So this gives us P is at most equal constant, n to the negative 5/6. But because, so any P that is smaller than this satisfies the second property. But because we want to choose the maximum lower bound, so we choose just n to the negative 5/6. So this gives us the first lower bound.
In that case, LF is just 5 or?
Oh, that's the number of edges, which is 6. Yeah.
Mm.
Well, it doesn't matter because L of f is just a constant, and we
So-
always ignore constant vectors.
But anyway.
Yeah. Any questions? And then we've seen, we know that we can do better if we choose U2 to be the densest part. In this case, the second calculation gives us something better.
Mhm.
Well, I think I can skip the second part of the computation now. Okay. Okay. So any other questions? Can I move on to our reformulation? Okay. Very good. We are on the way to the reformulation, and so here, this is the statement that we prove. Is this? Let me call this theorem prime. And this is, there exists some universal constant L. So I changed K from L because L is a different constant from K, but this is the universal. So there exists a universal constant L such that there is, for every L bounded hypergraph H into to the X, if P is larger than the expectation threshold for the offset generated by H, so this means just the expectation threshold for F. But because we want to replace F by H, so here I remove all of the terms that is relevant to F, so I just use H here. If we satisfy that assumption, then with M, which is defined to be L times P times log L times the size of X, so this is regarded as an integer. Not exactly, but we just assume that all of the large numbers are integers, just following some standard. Then with this number, the probability that xm satisfies the given increasing property h, this is 1 minus something that tends to 0 as L tends to the infinity. This is the reformulation that we are going to prove.
You have log L x, right? But it's log L times x.
Log L times x. Yeah. Let me give you 5 seconds to read this statement, and then I'll add some elaboration. So let's see what change. I'm not gonna derive this statement, give you the rigorous derivation of that statement from this statement, but let me just tell you what changed from there to here. So first of all, I think one change is we moved from this binomial model to this size model. And this is exactly said, this corresponds to, in the binomial model, this corresponds to the probability is L times P times log L. So this is exactly what's written here. So this is just change from the binomial model to this uniform model. And this is a standard change, and you don't have to worry about it. We can always switch from the probability to this size bound. And another thing is, okay, so in that theorem, we are interested in giving an upper bound on the threshold. And what does it mean by giving an upper bound? From the definition of the threshold, so this is the definition of the threshold. And giving an upper bound means if we are above this, then it's very likely that XP satisfies a given increasing property. So we want to say that if we are above something, then something is very likely. That's exactly what's written here. If we are above this range, then it's very likely that our random object satisfies the given increasing property. And the probability is very high, very close to 1. That's the meaning of this reformulation.
Okay.
Yes?
In this, in the reformulation, there's some, when you're looking at the expectation threshold, there's some family U there. Could you apply you could just, instead of using H, you could just use U here? Or is there something wrong with that?
No, so in this statement, so that U is for the definition of the expectation threshold.
Right.
And so
But if you can compute the expectation threshold, then maybe you could get your hands on a particular U that would have the same expectation threshold as as the offset of H.
Yeah, we can, I mean, so that's one way to attack this statement. So maybe if we want to prove such a statement, then maybe we can say that because P is larger than the expectation threshold, so there must exist some cover and P is above that, the value coming from that cover and say something, something, something. That's one way to attack this statement. Or maybe you want to say, so maybe you want to replace this by using the language of the cover. I don't know if that's what you meant.
Yeah, but isn't that a bit dangerous because the closure, or span, or whatever, the offset of U
Yeah.
could be bigger than offset of H,
Mhm,
right?
yeah,
So
definitely.
the last line, so the probability will be smaller, right?
So
If you
yeah, I think.
replace- If you
Right,
replace
I see.
offset
Yeah.
of U by offset of H,
Mhm.
then you have a smaller probability. So you cannot really assume that
That wouldn't
H is equal to U.
necessarily-
Yeah. Okay.
I see.
So in this statement, there's really no cover anymore. It's just statement about the expectation threshold and the threshold. But for the definition of the expectation threshold, we need to find, and we have the notion of cover.
I'm kind of wondering if you could replace this L of F with L of like an optimal
Something
cover.
you use is the cover, the size of the cover.
Yeah.
I mean, I'm not sure if we can do that because basically the biggest obstacle in proving this theorem is we don't have so much information about the cover. So
Yeah.
given the increasing property, we don't know what the best cover is.
I see.
So that's the obstacle. Okay. Any other questions? So are we okay with this reformulation or do I need to explain more? Yeah, please ask me questions because this is just a reformulation and I don't want to lose you here. So what we are going to prove is
the statement implies if the size of X is larger than M,
Mhm.
it's also going to satisfy the property. If
Yes.
that's true, that's because of our closure.
Yes, yeah.
Uh-huh.
So if M is larger, then that's favorable to us because this. Okay, what does this mean? This means Xm contains some member in H, right? So the meaning of this is, so this is our H, and the offset generated by H is this, and this means Xm is somewhere here. So if you look down, then Xm contains at least one member of H. That's the
Mhm.
meaning of this. So that means if Xm is larger, then it's much more, because it's more likely that Xm contains a member in H. Okay, so this is the statement that we are going to prove. And are you okay with this? So we want to show that if P is larger than this, then if the size is larger than this, then it's very likely that our random object satisfies this increasing property, which means it's very likely that Xm contains at least one member in H. Okay?
So there are some hidden assumptions, right? Like for instance, probability is not too big compared to L or something like that.
What do you mean by probability?
No, I mean the thing is, like L times P times log L.
Oh yeah, sure. So here our P is always very small because otherwise this statement is just trivial. Because this is about the probability. So if the right hand side is bigger than 1, then this statement is just trivial.
I
So
see.
that means this expectation threshold must be at least little of 1. So we always assume
okay.
that the expectation threshold is little of 1. So it's very small. Otherwise, the statement is just trivial. Okay, any other questions? Okay, so we want to show this likeliness. Okay, so what I plan today is I'm not going to present my proof in the linear order, and instead I'm going to show you, I'm going to start from a high-level picture, a rough sketch of the proof, and then I'm going to dig in our rough sketch and zoom in and zoom in and zoom in. And in that way, I think even if you miss a little detail of our proof, you can still see the high-level idea. So that's my plan. So let me start from the proof overview. And for this, so this is just the background. It's not very relevant to our proof technique, but I think it's good to know about some history. So let me start with the fractional Kahn-Kalai. And here we have exactly same statement, but our assumption is instead of having that expectation threshold, we have something called the fraction expectation threshold. So our assumption is p larger than the expectation threshold for h, or the upset generated by h. So this is the main difference. And what's good about this fractional version is if we apply the LP duality, then this assumption tells us something very nice about this hypergraph. So if you apply LP duality, then this assumption gives us H is something called spread. Well, I'm not going to define what this means, but roughly speaking, this is a very nice combinatorial property. This means this hypergraph H is not concentrated on a certain place. So this is very well spread in our universe. That's a rough meaning of spread, and this is a very nice combinatorial structure of H. And so using this assumption that H has a very nice distribution, we use this very heavily in our proof technique, in our fractional Kahn-Kalai. And our proof was built on the sunflower result by always Lobet, Wu, and Zhang. And from now on, let me call this ALWZ. And they made the breakthrough work in Erdos-Rado sunflower conjecture. And again, let me not explain what this is because it's too much abstraction. But let me just explain. So this is the starting point of this argument, and let me roughly explain what happens in this work. So what happens here, this fractional Kahn-Kalai is this. So eventually we want to show that our random object contains one member in H, and for this, we are not going to choose our random object at once. Instead, we choose our random object step by step. So we choose W, which is another name for XM, because I'm lazy, so I just want to use one letter. And we choose W little by little. So this is W is equal to W1 union, disjoint union, W2, W3, dot, dot, dot. And at the end, what we want is W contains some member in H. This is what we want. And pictorially, this looks like this. So this rectangle is our universe X, and our hypergraph H has a very nice property. This is spread. So the hyperedges are everywhere. This is well spread. And so this choosing W little by little means in the first step, we sprinkle our first random elements. And in the second step, we add some more random elements. And we do this by a certain number of times. And at the end, what we want is, at the end, if we take the union of all of the random elements that is sprinkled so far, then there exists at least one member of H that is contained in our final random set W. This is what we did. This is what we do in that work. Okay, so this is our goal, and I don't have.
So you have the same strategy, the fractional and then.
So here, not exactly similar, but not exactly the same, and I wanna show you the difference. So at the end, I'm gonna show you what's the main difference between that argument and our argument.
You can also use one below.
Here, can I?
No, there's one more.
Right here? Oh, yeah. And to achieve that goal, so we want to contain at least one member in H at the end. The dreamy situation is this. Okay, so we want to contain one member. Let me call this S in H at the end. And a dreamy situation is if we sprinkle our first random set, then so let me call this W1, and W contains 10% of S. So this is dreamy situation. And if we sprinkle the second random set W2, then we dream that maybe it contains 10% of the rest. And if we sprinkle the third random set W3, then this contains, again, 10% of the rest. And if this dreamy situation really happens, then how many iterations do we need to contain S completely at the end? It requires, yeah. So if this really happens, then W contains this S within the size of log of size of S steps. Maybe there's some constant factor. Okay, and this is where log L comes from. So basically what we do is, the size of each random set is K times QF, and we iterate this process by log L times, because the size is L, at most L. So this is a dreamy situation, but I want to emphasize that this is really dreamy. Because what's W? So as I said, to make this claim to happen, then the size of each random set Wi, let me say Wi, is L times P subset of X. Right? So that means each element in X is chosen by probability L times P, which is very small. So that means typical size of Wi union S, what's this? This is about LP fraction of S. And this is very small, real of 1, because as I said, our expectation threshold P is usually very, very small. This is little of 1. But in our dreamy situation, we hope that, or we aim for 10% of S. So 10% versus little of 1. So this situation is really dreamy. So I'm talking about what blocks us to achieve this dreamy situation. And the obstacle is this. Our Wi is too small. But what saves us is, okay, so in this dreamy situation, I mean, we don't need this to happen to all of the S's, right? So it doesn't have to be typical. We just need one S that is contained in W at the end. And that's what saves us. So we don't need this to happen to all of the S's, but we just need at least one S. Okay, so what, where is it? So what they did is exactly, they made this dreamy situation to happen for at least one S. That's their great idea. So in this work of ALWZ, in this work they achieved some amazing sunflower bound. Well, let me not give you the quantification of this sunflower bound. It's very long. But if we naively apply their argument to the fractional Kahn-Kalai, then it already gives us a very good bound, very good upper bound on the location of thresholds. So this gives us PC of F. This is at most K times the fraction expectation threshold of F times log of L of F. This is the truth, but they have some extra term, log of 1 over the expectation threshold. So if they didn't have this, then this is the right answer, but unfortunately they have this extra term. And so, for example, if the fraction expectation threshold is about 1/n, then this gives us an extra log factor. So again, this was an amazing bound, but in terms of thresholds, this doesn't give us the right answer.
So was it commonly known that if you have a good bound for sunflower, then you get the bound for this kind of thing? Or?
Oh no. So it's not exactly from directly from this, but if we use their argument as it is, then we can get. So if we combine our entire argument and their argument, then it gives us this bound. And here our main contribution. So let me call this F, K, and P. Frankston, Kahn, Narayana, and myself. So our contribution is just to remove this term. C of F is at most K times the fraction expectation threshold times log of L of F. And the main difference is, so here, I said the dreamy situation is to contain 10% each time, and that gives us log L iterations. But in their original argument, they didn't achieve that 10%. They achieved will of one fraction in each step. So their iteration is more than what is needed in our argument. So their iteration was more than log L, so they had this extra term. But in our argument, we used some extra argument to achieve that 10%. And then we got the right answer. So this is what happens in FKMP. And if we use our argument and apply this to the sunflower, then it gives us some little improvement. But this improvement is also improved by another group. So this is not the best upper bound. Okay, so this is roughly what happens historically what happens in the previous work. And let me make a little remark. Is that in this work, ALWZ and FKMP, in this work, really the spread, so I said using LP duality, we can say that H is spread, which is a very nice combinatorial structure, and this spread is really the main power source. So there are 2 points in our argument. The first point is to obtain 10%. And the second point is to show that we can actually iterate this 10% process. And in both points, this spread condition is crucially used. So we really can't do anything without spread condition in this argument. Okay, then now we are back to our main interest, the eraser. So now we are back to the ordinary Kahn-Kalai conjecture. And here our assumption is P is larger than the expectation threshold for H. And here, in this fractional version, we start from here, maybe even we start from here and we use LP duality and we get this nice structure. But if we start from the expectation threshold, then suddenly we don't know what to do with this. There's nothing to work with. So we lose our starting point. And you don't know what, we all know what it means by there's no starting point. We just don't know what to do with this assumption. So, and this is why, so I introduced, there is a conjecture by Talleyrand, and his conjecture is basically the expectation threshold and the fraction expectation threshold is equal to a constant factor. And so far, before our work, this was regarded as the most likely way to prove the Kahn-Kalai conjecture itself, because we didn't know what to do with this assumption. And then what we did is, so we used another algorithm. So this is what we did. And this algorithm is inspired by the original work by ALWZ. But the main difference is because we didn't know where to start, so we didn't assume anything. There's no assumption. Which means, as I said, in this argument, spread was really played a crucial role. So people use this spread condition in every corner of the algorithm. But because we didn't have any assumption, so we didn't have anything to use, which means we didn't have any power to steer our algorithm. So at the end, so no power to steer the algorithm. So at the end, what we showed is we have to allow two outputs. And then so one of those outputs is our desired result, and the other one is something else. And at the end, we add our assumption to show that the other one is very unlikely. And then that concludes this one happens very likely. We have this desired conclusion with high probability. That's what we did.
So you have some randomized algorithm that
That
has
output
two consequences.
Yeah.
One of them is good, one of them is not so good, but
There are two outputs, and one of them is desired, one of them is not desired. And we showed at the end, if we add our assumption, then it tells us that the not desired output is unlikely. So that gives us our desired conclusion is very likely. So what I want to say is the big difference between the previous work and our current work is, so there's no spread, there's nothing to use. So we just give up the assumption. Okay, so this is a rough sketch, and let me tell you a little bit more about this sketch. But are there any questions so far? Basically, I didn't say this is not real math yet.
I'm just, so you don't use the assumption until the very end?
Yes.
Okay.
Yeah. Okay. Let me tell you a little bit more about our algorithm. Okay, so I said our algorithm is inspired by ALWZ. So the starting part is the same. So this is what we do. Our random set W is the union of W1, W2, ... So this means we choose our random set step by step. And as we go on this algorithm, our hypergraph H also operates. So let's say our initial hypergraph is H0. And this, after we choose W1, we do something, and then after that, H0 updates to H1. And after we choose W2, we do something, and then H1 becomes H2, ... And at each step, let's say at ith step, what happens is this. So we choose Wi of size about L times P times the size of X. Let me remind you that our target size is L times P times log L times X, and each time we choose a random set of size this. So that means we have room for the iteration log L times. Okay, so we choose this set at random. And then, using this Wi, we construct a cover Ui. This is ith cover that depends on our choice of Wi. So this is a randomized algorithm, which means every choice depends on the choice of Wi. So depending on the choice of Wi, we construct a cover Ui. And what does this cover? This covers some Gi, which again depends on the choice of Wi. which is contained in our current hypergraph HI-1. And we are still in the sketch part, so let me not say how we construct this cover. So this is to be announced. But for now, I'm just giving you a sketch.
So GI is some family.
Yeah.
Oh, subfamily of.
So let me give you a picture. I love pictures. Okay, so here our universe is xi-1. So our universe also updates as we go on this algorithm. So now our universe is xi-1, and our current host hypergraph is hi-1. And those are the hyper edges in our hi-1. Then we construct a cover that covers some hyper edges in our current host graph. So this cover looks like this: here, here, and here, and maybe here. So those dots are the members of our cover UI. Then our GI is what's covered. This is our GI.
So shouldn't you say that it's a cover of closure or offset of GI? Or?
Oh no, GI is a hypergraph. So here, hi-1 is a hypergraph, so there are hyper edges everywhere. So there is no increase in family anymore. We start with the minimal elements.
Oh, so you just want to cover the minimal.
Yes,
Yeah,
so we just work with
actually,
the minimal elements. Yes,
That's
yes.
actually equivalent statement, right?
Yeah, here. Yeah.
If you cover the minimal
Eight.
element, you cover everything. So.
Yes, yes.
Right.
Yeah. Okay, so each time we construct a cover that covers some member of the current hypergraph. So in that sense, let me call this a partial cover. I'm just saying this partial because we don't cover all of the hyper edges. We just cover some of the current hyper edges. So this is what we cover.
So are you going to construct GI carefully as well?
Yes, yes. So this part is really, it requires a very clever argument. Yeah, we should do this very carefully. Okay, so we are gonna construct a partial cover of some hyper edges, and basically what we do is if we cover some of the hyper edges, then at this point we kick out all of the covered hyper edges, and then move on to the next stage using uncovered hyper edges. And so each time we try to cover some of the hyper edges, and once some hyper edges are covered, then we kick them out and move on to the next step. So as we go on, the number of hyper edges is getting smaller and smaller. Ideally, maybe it's not. We don't know what happens in the algorithm. But ideally, we are trying to cover some of the hyper edges inside. Okay. So this is our I didn't tell you how we constructed this, but let's believe that we can construct a cover. And do I want yeah, I think I can erase this part. So this is still not a real math. And okay, so this is our construction, and when terminates, and again this termination condition is not defined yet, and this is again to be announced. But there is a termination condition, and when terminates, then we collect all of the partial covers that we constructed so far. So with U defined to be the union of every partial covers. Either we have two possible outputs. The first possible output is first U covers the entire hypergraph H. This is the first possible output. Or the second possible output is W contains some member of H. And which one is more desirable? Which one is more desirable? Who thinks it's number one? Sorry, I was a middle school teacher. So who thinks it's number one? Number two? we have some good students and some better students. Okay. So this is our desired output, but there's no way to steer this because we don't assume anything so far. And now, the main point is this. Okay, so the main point is typically our cover, our partial cover use this. So this is still a partial cover. Typically, our partial cover U is P chip. If you still remember the definition of P chip. So P chip was here. Oh, it's still here. And this main point is to be proved. So now I owe you three things: TBA, TBA, and TBP. But once you trust that we have those three things, then we are done. Because now it's time to use our assumption. So once we have this, then what happens is, again, our algorithm is a randomized algorithm, and it depends on the choice of W. So let's say this is not X, this is the sample space, which means our choice of W. And for each choice of W, we see different outputs, right? And because of this main point, I said typically U is P chip. So that means for most of the choices of W, U is P chip. And for this little fraction, U is P expensive, say. So this is from our main point. Okay, for most of the choices W, U is P chip. And then we use our assumption. What's our assumption? Our assumption is here. Our assumption is P is larger than the expectation threshold of H. And how do we use this assumption? What's the definition of the expectation threshold? This is the maximum among all of the lower bounds. And how do we get the lower bound? Once we have a P chip cover, then the corresponding value of P gives us a lower bound, right? So P larger than the expectation threshold means there is no P chip cover. Right? This is from the definition of the expectation threshold. Again, how do we get the expectation threshold? This is the maximum P that for which there is a P chip cover. And because P is larger than that maximum, so that means there is no P chip cover. Okay, so this means if to have this, if one happens, then U must be expensive, because there's no P chip cover. So that means one is here. And what does this tell us? One is unlikely. So that means for most of the choices of W, we have the second output. So we achieve this conclusion. This conclusion. Do you see here? So we are done. Modulo 2BA, TBA, and TBP. Okay, so this is the end of proof overview. And I owe you three things. But are there any questions so far? So are we okay with this part, the very last part?
Or do we want to have a break?
Oh yeah, sure. Yeah, do you want to have a break? So, and maybe we can finish now and then you can check those three things at home.
How long do you want to have a break? 5 minutes? Or? Yeah, let's say 5. Okay, let's meet at like 5 minutes after 3.
하나만 질문 드릴까요?
네.
그 스몰 L 원저 텀이 중요한 건가요?
뭐 이렇게 이거의 값이 중요하냐고 물어보시는 건가요?
그러니까 저게 0으로 가야 되는 게 중요한 거예요?
왜냐하면은 보통 저희가 이렇게 주로 그러니까 저희 분야 랜덤 티어리에서 얘기를 할 때 보통 어떤 현상이
네.
그 with high probability로 일어난다라고 하는 게 사람들이 이제 사람들이 관심 있어하는 부분이고 특히 이런 에러 텀이 얼마나 작은지도 사람들이 관심 있어하는 부분이거든요. 그래서 이게 더 스트롱한 스테이트먼트고요.
네.
어떤 사람들은 이 값이 뭐냐에 관심 있어 하기는 해요.
근데 그 생각을 해봤는데
네.
예를 들어서 라벨드 그래프에서 처음 1부터 K까지 벌텍스들을 클릭으로 포함하는 그래프들의 인크리즈 프로퍼티이긴 한데 그거의 미니멀 엘레먼트 L은 K로 딱 고정되어 있잖아요. 그럼 이제 L이 무한대로 안 가버리면은
네. 근데 이게 어차피 쟤를 임플라이 하기 때문에 예. 그래서 L이 무한대로 안 돼요.
L이 고정되는
예, 그렇죠. 예, 그러니까 이게 참이면은 저것도 참이고, 그래서 예, L이 굳이 무한대로 가지 않아. 근데 그 차이라면은 이 경우에는 그 probability가 1로 텐드 하는데 L이 고정되면은 그 definition은 그 2분의 1이잖아요. 그래서 이 경우 I think
Okay.
I'm doing too slow.
I gotta do all that stuff.
We have
Yeah, I mean,
plenty of time.
Yeah, but I still have one more hour.
That's what I'm doing.
Alright.
Before I go home.
Actually, I'm slightly confused there at the end.
Uh-huh.
So what I'm confused at is you have these two outcome.
Uh-huh.
One of them has to happen, right?
Yes.
The first one is U is a cover.
Oh, yes.
Then
not a
you said that
cover.
by definition of P,
Mhm.
there's no P chip cover.
Yes, but it's typically. So that means for some choice of W, it's possible that U is expensive, but typically it's cheap.
No, but definition of P means there's no P chip cover, right?
Uh-huh. Yeah, there's no P chip cover, so that means that happens here. U is expensive. So this is a sample space of W, and for most of the choices of W, our U is P chip. And sometimes U is P expensive. So if U covers H, then by our assumption, U must be expensive. So that means U falls in this small area. So only for those choices of W, U can be a cover. So that means it's unlikely. So this main point does not say that U is always cheap. It says that typically U is cheap, but sometimes U can be expensive. And if the first outcome happens, then by our assumption U is expensive.
Oh, okay, I see. So I guess what I'm confused at is when U is P cheap, then it cannot be a cover.
Yes,
Oh, okay.
because a cover is always expensive by our assumption.
I
Yes.
have a question. So just not confusion. So is it true that as long as you prove that U is P chip with positive probability, that's good enough? Or do you have to prove it?
Oh, because we want this statement. So we want to show that this probability tends to 1. Yeah, so we want this. Yeah, of course, for this, maybe we don't have to show this probability tends to 1, but it's an interesting statement in our in the random reference. Okay, are there any other questions? Okay. Then, as I said, I owe you 3 things, and so the first one is construction, the second one is termination, and the last one is the main point. So let me start with the construction part. I need to find the eraser. Okay, so this is the construction of the partial cover UI, which depends on the choice of WI. And our current host graph is called HI minus 1. And let me say this is S bounded, where S is just anything. So this is a finite set, so there must be some maximum for the size of the hyperedges here, and we just choose say that is S. And we use S, S prime, and S hat for an element in HI minus 1. So we always assume that S or its variant is a member in HI minus 1.
So what's the reason why you use small s instead of L? Do you change?
Oh yeah, because as we update our hypergraph, this boundedness changes. It decreases by little by little. So we don't want to use L. So we just use this general letter. And so we want to construct a partial cover, and what we do is we examine each S, where S is always a member in our current host graph, and then we decide whether to cover it or not. And this is the clever part. So this is how we construct, how we decide whether we want to cover S or not. So this is our choice of WI, and this is the given S. And typically their intersection is very small, little of 1 fraction. We talked about this before. And so in this picture, what we do is to look at all of the members of the current host graph HI minus 1 inside WI union S. let me just say W is Wi, just for simplicity. So in the current picture, we look at all of the members of the current hypergraph inside W union S. So maybe there's something like this. Let's say this looks
So
like
in other words, you look at the subsets of W union S.
no, we look at all of the members, so specifically the members of Hi minus 1 inside. Among all of the subsets of W union S, we look at the elements in Hi minus 1, yes. So maybe it looks like this. So those are the members of the current hypergraph. And then we give a special name, let S prime to be the something inside W union S that achieves S prime minus W is the minimum. So maybe we see a bunch of S primes, a bunch of elements of Hi minus 1 inside this union, and we choose this S prime for which this part is the minimum among all of the hyperedges inside this union. And because this is so special, so we give a special name. So this is the key definition. We define T, we say T, which is a function of W and S. This is defined to be S prime, where S prime is that one, minus W. And we call this the minimum WS fragment. And this is really the crucial object, the crucial gadget that drives our entire proof argument. Okay, and once we define this minimum fragment, then it has some very interesting properties. So let's say this is our choice of W, and let's say we have T, and this is somebody's minimum fragment. Then what we know is, first of all, let's see if you agree with this. There must exist some member in Hi minus 1 that is contained in W union T. Do you agree with this?
S prime satisfies
Yeah.
that, for example.
Yeah, exactly. Because this is somebody's minimum fragment. So there must
Right.
exist something that looks like this. So this is just trivia from the definition of the minimum fragment. And the second one is really interesting. And this is very crucial in our proof. For every S hat inside W union T, T is contained in S hat. Do you believe this?
Mhm.
By the minimality. Because otherwise, if something looks like this, then it gives us smaller minimum fragment. So once we have the minimum fragment, then the picture looks like this. Whenever we have an element in this hypergraph, it always looks like this. So T is really the core part of all of the hyperedges inside W union T. And why do we, so where do we use this? We use this is a rough picture. So where we're going to use this is, eventually we want a chip cover. So we want, this is the main point, we want U to be chip. So we want to find a way to find the chip cover. And for that, this is just a rough idea. What we're going to do is we choose W union T first. And this one is relatively cheaper. And here we're going to find T. And as soon as we find T, we can find W. That's our goal, but you'll see why. But for now, you just trust me. So we first specify W union T, and then we're going to find T. But if T is just in any place of W union T, then finding T is just too expensive, because we have to search for all of the subsets of W union T. But because T is the minimum fragment, so that means once we have W union T, then we just pick any member S hat in our current hypergraph Hi minus 1. And because we have the list of our hypergraph, we can always choose one inside this. And once we pick S hat, then T is always inside this small S hat. So this makes finding T much cheaper than this generic idea. And we're gonna use this idea to show that our main point, typically U is P-chip. But we'll get there at the end. So this is the idea, this is some rough idea, parenthetically. Okay, so still we are still constructing a cover, and okay, then how do we decide whether we want to cover S or not? So let's say S, I need a space, so let me move on. We say S is good if T is large. Here large means it's larger than 0.9s. And if we have a large T, large minimum fragment, in this case we cover this S, because in this case T is relatively cheap. So we put T inside our partial cover, and then we put S in GI, and by doing this, we just kick out S from our universe. So yeah, so this is the picture. This is our X, and those are our hyper edges, HI minus 1, and then if this T is large, then we put this in our partial cover, and then we just kick out this hyper edge, because this is already covered. And otherwise, if T is small, in this case, if T is small, then this is expensive. So we can't afford this cover, so that means we just keep it. So we put T in our next hypergraph, HI.
Why large is cheap?
You'll see that at the end. So if it comes, I think it's better to give you the quantification rather than giving you a rough idea. Yeah, roughly speaking, large T is cheap because if T is too small, then our gain from this choice is not very much. So when T is large, we can gain by choosing W union T rather than choosing W and T separately. But you will see that computation at the end. And the meaning of this is, so if this T is small, then we replace this S by this little T. So this, by doing this, our hyper edge, the size of our hyper edge gets smaller and smaller as we iterate this algorithm. Okay, let me move on. I think it's better to give you 3 points of this construction. So there are 3 points, and let me explain a little bit more after I write down these 3 points. First of all, if HI minus 1 is S-bounded, then our next hypergraph, HI is 0.9s bounded. So the boundedness is getting smaller and smaller. If we started from S-bounded, then the next hypergraph is 0.9s bounded, because we always either we cover one S or we replace this by its minimum fragment. And because this case happens when T is smaller than 0.9s, so S is replaced by something whose size is 0.9s. So always we have the size of hyper edges are getting smaller and smaller. And we need this condition to terminate this algorithm. And second point is a cover of our next hypergraph, HI. This also covers HI minus 1, the previous hypergraph minus the things that are kicked out. So those are the leftovers. And do you trust this? A cover of the next thing, the next hypergraph, HI covers the leftovers. This is because in this algorithm, S is replaced by something smaller. So if we cover this thing, then of course this covers the larger thing. So always a cover of the next hypergraph covers the leftovers from the previous graph. So this says that U2, U3, U4, those are all partial covers.
So HI are the fragments that are uncovered.
Yes.
So you're shrinking the fragment area.
Yes, exactly.
Oh.
H. And because of 2, we can say that we can iterate this algorithm. Because each time we construct a cover of the current host graph, then it covers the initial host hypergraph. So we can safely iterate this algorithm. So the second one is this. Okay, so the first one is needed to guarantee that this algorithm terminates, and the second one is needed to show that we can iterate this algorithm. And the last thing is our main point. Again, this is to be proved. Our main point is for typical choice of W, the summation U in UI, P of U, this is L to the something very large. So this corresponds to the definition of P chip. So this says that each partial cover is P chip, and at the end, even if we combine all of the partial covers, they're still very cheap. They're still P chip.
Here
So
the quantifier is for each I.
Oh yeah, for each I. But because this is exponentially small, so even if we add up all of the costs, at the end it's still very, very cheap. So each point has its own meaning. And this is our construction. So we are done with the construction. And are there any questions about this construction? So this is our construction of the partial cover, and those are the points of this construction. And the next thing that I owe you is how we terminate our process. And let me define the termination condition. And don't worry, I only have 2 slides left. So the next slide is about the termination condition, and the last slide is about the main point. And the proof of the main point is 3 lines. Just to cheer you up. Hang in there. And then termination condition. We finish this termination, this algorithm as soon as either GI is HI minus 1. So that means we cover everything in the current host graph. So this corresponds to U, which is the union of UI. This covers H. So this is our first output. Or T, the minimum fragment, is the empty set for some S. So pictorially, this means we have our current WI, and we have our current S, some S, and there is some S prime that is entirely contained in WI. And if this happens, then this means W, which is the union of WI, this contains some member of H, right? Because each time we shrink our S, and the way we shrink that is, so here we have this W, and we have this S, and we replace S by its minimum fragment. So that means the rest of this minimum fragment is already contained in some W. So if this happens, then this means the rest of S prime is already contained in the union of WI. So this corresponds to this W contains some member of H. So this is the second output, which is desired conclusion. And so then how do we guarantee that our algorithm terminates? I claim that this iteration terminates within about log L steps. And this is because of our first point. Because each time we shrink our size by 0.9, so if we iterate our algorithm by about log L times, then the size is less than 1. So that means eventually either this happens or this happens. Okay, so this gives us the guarantee that our algorithm must terminate within log L steps. So that means at the end, the size of our random set W is about L times P times log L times the size of
Just to double check, I mean, if H is not, I mean, this union of H or HI is not exactly a subset of H.
No,
but
no, not
it's,
at all.
It's
Yeah.
okay because we can conclude the second. That's because what we add T is something special. I mean, if we
Because T is a so
T
because
already
each time
is-
T is a subset of S, the
Right.
previous one. So if we cover T, then it covers the first one.
So I'm just asking the second conclusion that
Yes.
you made, like or. Yeah. So the second conclusion, I mean, naively I thought initially like because this H, if that happens, so then there must exist some S, because H remains the same, but it's not like, I mean, something that we add to H, like a T in this otherwise case. Is there something?
Oh yeah, because T is the minimum fragment of S,
So-
and so that means if we contain T, then the rest of T, so rest of T means its original piece
Yeah.
is already contained in some previous steps.
Right.
Yes, so that's why we have, this implies W contains the entire piece of this, the original piece of T. Yes. So yeah, so there is something subtle, and this is very delicate algorithm, and so that's why the construction must be very careful and clever. Okay, so this is the end of the proof modulo the proof of the main point. So this is end of proof modulo the proof of main point double factorial. So I owed you 3 things, and I just gave you the first thing and the second thing. And now we are left with the last one, proof of the main point. Okay? Okay, are there any questions before I prove the main point? Okay, proof of the main point. I don't want to miss that one. Oh, good. So this is the final piece, and let me write down the quantified version of the main point. Okay, with the size of x equals n, and W is L times P times n, and H is S bounded, we will show that the summation W inside X choose W, summation U in the ith partial cover of U, P to the size of U, this is at most n choose W times L to the minus 0.8s, where this 0.8 is really not important. It's just a convenient choice. So this is the quantified version of the main point above. Why is that true? Because so W is a set of X, a subset of X size whose size is W, and this is why it's convenient to consider this size bound rather than the binomial choice of W. So the number of choices for W is exactly this. So basically this says that on average, the cost of our partial cover is this. So this is the average cost for our partial cover UI. And it shows that this is this cost. So this cost is exponentially small. So this average cost is, of course, less than 1/1/2. So this says that on average, this partial cover is very cheap. Not just 1/2, but it's exponentially small. So once we show this, then we are done. Because it says that typically our partial cover is P cheap. Of course, here we have to use the Markov's inequality to show that this is a typical behavior, but let me, would you like me to write down this Markov inequality? I think it's fine. So on average, this is very cheap. So typically, it's very cheap by Markov's inequality, if necessary. And this is the most advanced technique that we require in this proof, Markov's inequality. Okay, so this is our goal, and as I promised, the proof is just 3 lines. First of all, okay, so proof is double counting. And we're gonna do this only for the size of u equals 0.9s. So here, u is in ui, that means the size of u is at least 0.9s, right? Because only in this case, we put u in ui. If u is smaller than 0.9s, then we don't cover that s, we just replace s by its minimum fragment. So everything inside our partial cover has size at least 0.9s. That was our construction for a cover. Here.
So
Yeah, sure.
this W in the outer summation, that's basically the WI, right?
Yes, yes, yes.
So
yes.
don't you have to exclude already chosen elements in
Do I have to exclude what?
like you have already chosen like W1, W2, W3. So don't
Oh yeah, but
or
because
it's not important probably.
yeah, it's not important because the size of W is little of 1 fraction of So let
So
me.
X is always not really changing except for.
Yes,
you just
exactly.
look up to it.
Yeah.
So it's-
Yes, that's true. I try to hide that minor detail, but you're right. Okay, so we do it only for this because once we know how to do this for this size, then we can apply the same argument for different sizes of u, and at the end we just sum up all of the cost. And because this average is exponentially small, so even if after we add up all of the costs, it's still exponentially small. So it's enough to show this for this fixed size. So exponentially small is a magic word. Okay, so once we fix this, then what's the left-hand side? Because the size of u is 0.9s, so we can pull out this part. Then that becomes p to the 0.9s, because the size of u is 0.9s. And then we have summation w in x choose w, summation u in uiw, and then 1. The left-hand side, we pull out p to the u, and p, because u has size 0.9s, so p to the u just becomes p to the 0.9s, and then we have this.
Oh, this is why large is cheap, because
Yes.
power becomes larger. That's the question I asked you before.
No, the key point, the key part is here. Yeah. Maybe we can talk
Okay.
after we finish. Okay, then what's this? So this means whenever we have a pair that consists of one W and one U, we add 1. So this is basically the number of pairs, W. And what is U? U is always a minimum fragment of somebody, right? So we basically count the pair of W and T, where T is a minimum fragment of somebody, where W is inside X choose W, and S is a member of the current hypergraph, and the size of this minimum fragment is precisely 0.9s. This is what we count. So each time, so this means we add 1 for each pair, W and U, but U is always a minimum fragment of somebody. So this pair is just W and T, where T is a minimum fragment of some S. So W is from here, and this T is somebody's minimum fragment, and the size of this minimum fragment is 0.9s. So this is the final step. So 1, 2, 3 lines. The final step is, okay, so in choosing this pair, what we do is we first choose W union T. And the number of choices for this is n choose W plus 0.9s. This is a choice for W union T. Because W union T has size W plus 0.9s. And then once we choose W union T, then we choose T. And here comes the power of the minimum fragment. So once we choose W union T, then we see what S hat is inside. Because we have the list of our hypergraph. So we can fix one S hat, then T is inside this S hat. From, where is it? Key definition, and I think there is something I said crucial. Oh, crucial property number 2. So the number of choices for T is at most 2 to the S. Because we just choose a subset of S. And then what's this? Here W is there, L, so now this is quantification. So this is computation. This is n choose LP n plus 0.9s, and you can very easily check that. This is at most n choose W times LP to the minus 0.9s. Let me not justify it. I mean, I can justify, but I feel like you are exhausted, so let me not justify this part. If you want, I can do that. But for now, let me skip that justification. This is just this computation times 2 to the s. And we are done. Because we cancel out p to the 0.9s and p to the 0.9s. And then now we have n choose w, which is the first term. And now the computation is between L to the minus 0.s and 2 to the s. But L is a large number. So L to the 0.9s always beats 2 to the s. So this part is at most L to the something slightly smaller. So we are done. And this is why we need a large fragment, because we want to compute L to the something smaller than s with 2 to the s. So actually 10% can be better. It can be any b omega of 1 fraction, but we cannot do better than that because we compute L to the something and 2 to the s. So we at least have something negative big omega of s here. So we can't do better than 10%. But on the other hand, 10% is the truth. We can't avoid log L iterations because we have the tight examples. Okay, anyway, so this is the entire proof idea, and so we still have 15 minutes left. And so I wonder if you have any questions.
Could you tell us about this 2 to the s again? I mean, the size of s, I mean, in general can be larger than this small s, but maybe you...
This is at most 2 to the s. So we just, so here inside s, so this has size at most s. So the number of choices for t is at most the number of subsets of s, which is at most 2 to the s. Because the size of s is smaller than s.
The size of s can be, potentially it can be large, but you can always replace it by something smaller than s.
Oh, so here my assumption is h is s bounded. So this is for a fixed step. So if we have this s bounded, then the cost is always exponentially
So
small.
s bounded doesn't mean it's I mean, its minimal element is at most.
Its largest element is at most something. So S-bounded means every element in H has size at most S.
Okay.
Yes. Yeah, I think I lost some of my audience at the end. Are there any questions? Yes.
Can I ask just like maybe this is a sidetracking a bit. So this idea seems to be very crucial for that calculation, right? Like you count the this number of s in a very particular way. Like is this like this? Although this seems elementary, I don't think this is like I have never seen this type of thing. Like is this
This is what we
motivated?
this is what we invented.
Ah, nice. Okay, so that was what I was wondering.
Yeah. So yeah, so one crucial improvement over the previous work is the invention of this notion of minimum fragment. Yeah.
It's kind of completely mysterious until the very last line. Why are you looking at T?
Yeah, but yes, it turned out the second property especially is very crucial in this double counting argument.
Right.
Yeah.
Look at that last calculation. I'm sorry, this is a dumb question, but it looks like you're canceling p to the 0.9x and p to the minus 0.9s.
Yeah, because p to the 0.9s, p to the negative 0.9s, so they can cancel out.
Oh, right, that's multiplied through.
Yeah.
Okay.
So eventually those two cancels out.
Yeah,
What's
yeah, yeah.
competing is L and 2.
I see.
Yeah. Would you like me to justify this part?
So just to understand better, so I would like to estimate the number of this possible sets. You were counting like a larger set first, like this, okay, I don't know what I'm trying to do. So you were trying to somehow count the number of sets of size 0.9s, right? With
You mean here? So here, one point is we choose W union T instead of choosing W and T separately.
yeah, exactly. So in order to do that, you were looking at a bigger set and then choosing all possible things there.
Yeah, so we choose. So we look at the universe. So here we have our universe, and inside here we choose every set of size W union T. So there is. So this is an overcounting because we want an upper bound. So it's possible that some set of size W union T is not exactly W union T, but we don't care because it's an overcounting.
So in the fractional version, you have the spreadness to help you to drive the argument.
Yes.
Once again, can you say the difference of these two here? You don't have the spreadness.
No. Yeah.
There, it helps you to bound the number of choices, right?
Maybe that's a good question. So what they do is, okay, so in our previous work in FK and P, what they do is, not here, where do I, okay, maybe this one, not this one. Okay, so here we have two desired outputs and, okay, so if, okay, that's a good point. So if T is large, then we recover that S. So that heads towards the number 1, the first output. So if we have a large minimum fragment, then it is heading to number 1. And if we have a small minimum fragment, then it is heading to number 2. So small minimum fragment is desirable for our purpose. So in the fractional version, what we did is show that this large fragment is unlikely using spread. So spread is used to show that large minimum fragment is unlikely. And then once we show that, we just kick out all of the large minimum fragments instead of putting it inside something. So the point of our current argument is somehow we found a way to use both sides of minimum fragment. If this is large, then it plays a role, and if this is small, then it plays another role.
And you said W is growing at each iteration. How much samples?
So Wi is always L times P times the size of universe, and at the end we take the union of all of the random Wi's. So at the end we have this entire W, which is a union of the random set from each step.
So each round, this W that you described here is W that's chosen in the particular round.
Yes, 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 yes. So I fixed each round and then I explained this construction. Yes.
So you had one work where the square root of Hamilton cycle where the iteration is less. So
Yeah.
what combinatorial property you can define to reduce the iteration?
Oh, okay. So that result uses our fractional version argument, not the current argument. And in the fractional version, so in the square root of Hamilton cycle, the spread is not uniform. So the maximum of the spread is like, so typical spread is much smaller than the maximum spread, and somehow we used that part.
Is there an integer version here?
That's a good question. And integer version.
Like, can you do this method on that problem?
For now, I don't have that in mind. So I don't see what corresponds. So in the spread version, we use this non-uniform spread. But in this integer version, I don't know how we can use the notion of cover for this square root of Hamilton cycle. That's a good point. And I don't see immediately how we can do that using this integer version.
So I don't think you intended this as really an algorithm, but suppose I use this as an algorithm to find, reasonably small set that satisfies some constraint or some property, then how long does it take? Or
Log L.
no, each iteration it costs quite a bit because you look at everything and.
Yeah, so each step, what we have to do is to examine all of the elements in H. And then we have to take a look at the minimum fragment. And then we decide whether we want to cover it or not. So each step, that many steps happens. So it's each step, at least we have to examine like the size, as many as the size of the hypergraph.
Do you think it's possible to optimize? If I just want to implement this solver,
But
Step is still linear time, right? Proportional to the number of edges.
Yeah.
Yeah, so then number of iterations is
Yeah.
log of s.
so the primary is the size of the hypergraph, and it's linear.
okay.
So it's going to be difficult to be faster than linear.
This is linear, yeah, not linear because once we have one hyper edge, and then we also have to examine all of the hyper edges corresponding to that given hyper edge. So it's square.
Oh,
So
okay,
yeah, it's
quadratic,
polynomial.
okay.
Yeah,
Yeah.
quadratic.
Mm.
So it's not bad. It's not exponential. Do you have any other questions?
Can you characterize some increasing properties for which the bound is not tight?
Could you say that again? I didn't hear you
Can you
clearly.
characterize some increasing properties for which the bound is not tight?
That's my goal. So that's the thing that I explained yesterday. You know, at the end I said we want to characterize the size of the gap between the expectation threshold and the actual threshold. And so far, yeah, we have some test cases and we are still there. So we are trying to solve some test cases, and from there we want to find the characterization for the size of the gap. Yeah.
You think the only thing you think that you could always maybe explain what goes wrong by this coupon, some kind of coupon collector issue?
That's our that's our like.
I mean, I don't know exactly what that would mean, but.
Yeah. So yeah, I mean, so this iteration definitely tells us that the coupon collector behavior gives an upper bound, because what happens here is each time we collect like 10% of S. So so we collect little by little. So at the end, to collect the entire S, we have to iterate this log L times. So that I think that corresponds to this coupon collector behavior. But as we see, sometimes this coupon collector is not tight. So I don't know how to explain that phenomenon.
So
You promised you're gonna ask many questions.
well, yeah. So I'm thinking of some kind of so we have now proof, but can we use in a slightly different situations where for certain elements. Yeah, so we have this p to the u, right?
Yes.
So, and so threshold is here. Is threshold is like every element can appear with the probability p, right?
Mm-hmm.
But now let's say I pick some subset, and those subsets I always appear with the probability half.
Okay.
So some
So you
element-
plant something.
Yeah, so I have already some subgraph, or
Uh-huh.
I already have some random subgraph with a certain probability.
Uh-huh.
So you put the other things on top of that.
Oh.
Still, you may wish to know the threshold, right?
Oh, yeah.
So then this, what is, I forgot the name, the expected threshold?
Yeah, expectation
yeah,
threshold.
We need to change the definition, right? So because whether or not this element belong to my fixed set
Mm-hmm.
or outside of set changes whether or not you put like half to the something or
So
p
maybe
to
we can
something.
simplify this problem by deterministically flanking something and then think
Yeah.
about the other things. No, maybe in that case. It depends on what we want to plant.
Right. I mean, I remember that there's like, if you start from any spanning, so if you start with a spanning tree and keep adding edges, then
Uh-huh.
suddenly you have a different threshold for many
Yeah, sure.
properties. And I wonder whether the current theorem already implies such a thing, or some variation of this expected threshold function.
Yeah, I think in that case, I mean, I can think of, so we can maybe there's a way to handle that problem using our fractional version argument, because that's easy, because we just need to find an upper bound on spread. So if we have this planted graph, then what's left is what's the spread of our, like, of the given family, given we planted some structure. I don't know if I'm making sense, but anyway, but for this integer version, in that case, how do we? I don't know for now. Well, yeah, I think that's an interesting question.
All right. Any other questions?
Is there a characterization where the spread is not uniform?
Oh yeah. So I heard, it's just, yeah, there is a recent work about a Steiner triple system. So some group of people found the threshold for Steiner triple system, and there they said they used the non-uniformity of spread. Oh no. So what's your question?
The question is there a characterization for the property where the spreadness is not uniform?
Oh yes, so one example is the square of Hamilton cycle. Their spread is not uniform.
Right, but why it's not uniform? Apart from doing the calculation.
Oh yeah, that's because of the definition of spread. Because the definition of spread uses all of the subsets. We don't just look at the entire like object, but we also look at some part of the object, and there is a way to compute the spread, and it depends on what size of subset we look at, and then we see our computation tells us the spread is different depending on what object we are looking at. I can tell you more after this talk. Yeah,
Okay.
that requires the definition of spread. Okay, so
Is it not all the questions? All right. Then let's thank the.